want to speak of perceptual learning in the context of top-down processing. And there's an experiment that demonstrates it by the Gibsons going back to the 50s. And this is one of those early cognitive experiments that has stood the test of time now for roughly 70 years. They analyzed participants' errors on a task, and they found that the errors were not random. So here's what it is. A classic study by the Gibsons illustrates this. Participants, both children and adults, were shown a card in the very center. And here's that card. For about 5 seconds, and we'll call this the original. Next, they were shown other cards, and randomly mixed in with these were 4 copies of the original along with those other cards. The participant's job was to identify any instances of the original in the deck, and there were 4 of them. They received no feedback, but after seeing all the cards, they were shown the original card again for 5 seconds and then showed the full deck of cards in a new order. And they continued until each person correctly identified each of and only the 4 originals without being fooled by the distractors. So back to this paragraph. When they analyzed the errors that the participants made on the task, they found that the errors were not random. Rather, the number of errors seemed to depend most on the number of similarities a stimulus shared with the original. And they were more likely to falsely recognize a stimulus that had the same number of coils and was oriented in the same direction as the original than to falsely recognize a stimulus that had only the same number of coils. So in order to get good at this, what's going on? Apparently perceptually practiced individuals learn what aspects of the stimulus attend to and to try harder to consciously distinguish between different kinds of stimuli. With regard to top-down processes, a perceiver's experience appears to help guide what they paid attention to among these coils to pick up more information, to block out the relevant things or block out the irrelevant things and pay attention to the relevant things. Do you know what I consider when I'm thinking about this? I happen to be an enthusiast about watches. If I had money, and I don't have a lot, but if I were a multimillionaire, I would love to go get a good handful of expensive watches, and my favorite brand is Rolex, although there are others like Patek Philippe and some other interesting ones. And what is it about these watches, the discerning horologists, as they call it, what makes them valuable? Well, there are a handful of key features. You know, one of them is a sweeping second hand. It doesn't tick, but it sweeps in a smooth way. Other particular things about the dial and the crystal that are very suggestive of extreme high quality. Now, I've never had enough money to buy one myself, but I do think after watching roughly 10,000 YouTube videos on watches, I think I've got a pretty good feel for what would stand out as a legitimately very expensive watch that would be above $20,000. And of course, not something I would ever have, but still, if I do hit the lottery, I'll get 1 or 2 of them. So among watch enthusiasts, horologists as they call them, it would be the case that you have this discernment. You have finer features that you learn to pay attention to and disregard other things as these people got good at discerning these cards. A word superiority effect. Interestingly, participants can much more accurately identify letters presented in the context of a word than alone. It's called the word superiority effect, going back to 79. They're apparently easier to perceive in a familiar context. So, for instance, if each of the things on the left was flashed very quickly, either you got K alone, K in the context of work, or K in the jumbled array, we'd be very good at identifying the K in the context. The word adds something to the perception of it. And that's a fascinating top-down process that suggests I'm processing the whole thing within context and able to see it, especially when things are presented very, very fast. You know, we have software now that's widely available that will present a stimulus at, I don't know. I believe it's, if I remember right, 1/60th of a second. That's a screen refresh rate. 1/60th. So that's pretty darn quick, and it's very difficult to see. And that's where you can begin to evince these effects. You can see it, the K presented in the context of work and come out really, really quickly. So that's kind of cool. Do you know, your text throws in a couple of these spaghetti-like models. Rumelhart and McClelland is very accomplished in this, speak of, sorry about the coughing, a connectionist model of word perception. We spoke of connectionist models in the first chapter, but I want to just allude to it here. And these kind of look like spaghetti, but here's the idea. Once a node is activated, and a node is sort of a metaphor for a neuron or a group of neurons, really. Once a node is activated, that activation spreads along the excitatory connections to other nodes. And let's say if the trap node has an excitatory connection to the T node, then the T node will become more active when the trap node becomes more active, and vice versa. So these excitatory connections are represented in 3, 2, 1 by blue arrows ending in points, and the brown lines ending in dots indicate inhibitory connections. So the line between the trap node and the able node. If the trap node is active, the able node becomes suppressed. If you perceive trap, you're less likely to perceive able, and at the same instant. So this is a little subdued. Your text has a better illustration. She gave me this as part of the PowerPoint notes, and it was kind of a little cruddy. But as you can see, some of the links are brown and some are blue. If I've activated trap over here on the left, then able tends to be inhibited. And you can see I've got common letters there, T and A, and some other things that are activated as a function of what I've perceived. And the broader model is here. In this case, here's 320. Figure 320 illustrates that some of the processing levels that the model assumes, and it assumes a lot, but it's been validated a lot by experiments. Note that the model assumes that input, whether it's written, spoken, or of some higher level, such as just the context of an expectation, is processed at several levels within the terms of features, letters, phonemes, or words. And the many arrows in the diagram, so it is rather complicated, they manifest the assumption that the different levels of processing feed each other. And each level of processing is assumed to form a representation of the information at different levels of abstraction. So I've got features like Paris in the spring, all of the P and the A and the R and the I and the S, but it also sets up an expectation for words. And me leading to the conclusion that phrase was there, even though it was degraded by a typo of the word the appearing twice. So what you have here is the more general model, followed by a really specific model here for how we might recognize one word above another. It involves a lot of faith from the observer. These models are terribly elaborate, but they've stood the test of time because they tend to represent data pretty well neurally, etc. I may have told you my dissertation taps the modeling of a real cognitive process that I observed with real human participants, which was a pain in the neck, but I got through it, and I think it's a pretty solid dissertation despite that awful typo that's on the first section.